Welcome to this explainer presented by Forge College. Now, if you've been following our track on transitioning from EVM to SVM, you know we've been deep in the trenches of Solana and Anchor. In our last lesson, we mastered Anchor upgrade flows and practices. But today we're going to treat Solana smart contract upgrades like a high-stakes engineering disaster drill. We're talking versioning, testing, and rollback strategies. All right, let's dive right in. Here's our blueprint for today's drill. We'll be hitting the upgrade danger zone, building the test harness, breaking things on purpose, the rollback scaffold, verifying the rollback, and finally, debug reports and next steps. Okay, part 1, the upgrade danger zone. So we really need to establish why that old Silicon Valley motto of move fast and break things is an absolutely terrible idea when you're handling millions of dollars in total value locked on chain. Upgrading a program on Solana is frankly a lot like swapping an airplane engine mid-flight. It adds massive risk because your new code might have hidden logic errors or maybe unexpected state mapping mismatches that only pop up after you deploy. Now, in the EVM world, you might just use proxy contracts to handle this, right? But in SVM, we're actually replacing the program binaries outright. If you mess up the state transition here, that plane is going down. To manage all this chaos, we use what's called a migration entry point. The crucial thing to understand here is that this entry point acts as an observable breakpoint. It's invoked by a script to safely transform your on-chain state during an upgrade. And for our disaster drill today, this entry point is our main target. It's exactly where we're going to introduce our controlled failure. Moving on to part 2, building the test harness. We obviously need to set up the scaffolding to simulate our disaster safely without risking a single drop of real funds. So we're using a minimal project scope here. Take a look at this setup. We've got lib.rs acting as our Rust baseline and migration stub. Then we have broken_migration.ts, which is our deliberately broken TypeScript migration. We've also got upgrade_rollback.test.ts for our mocha or just tests to actually catch the failure. And finally, the real hero of our story, rollback.sh, a bash script designed to save us when things inevitably hit the fan. Our local test harness is going to run through 3 distinct steps in a very strict sequence. First, we deploy the baseline program so we have a known good state. Second, we run that deliberately broken migration to simulate an upgrade failure. And third, we execute our automated rollback. We do all of this to make absolutely sure our parachute actually deploys when we pull the cord. Which brings us to part 3, breaking things on purpose. All right, now for the fun part. We are going to intentionally break our smart contract like a burnt pie left in the oven way too long. In our TypeScript migration script, we're going to simulate a critical failure. Let's imagine our account has an expected positive value, say 42. We're going to intentionally mismap this numeric field during the upgrade script, and that's going to force that expected positive value all the way down to 0. Now, why does dropping to 0 even matter? Well, it's all about invariance. An invariant is basically a non-negotiable rule about your program's state that must logically hold true at all times. So when our expected value of 42 unexpectedly drops to 0, it completely violates a core invariant of our program. This violation instantly triggers an assertion failure in our local test suite, setting off every alarm we have. That moment when value equals 0 and you realize you just wiped the state. I mean, talk about a cold sweat panic-inducing realization, right? It is the exact moment you realize your newly deployed migration just bricked your entire application. And guys, this is exactly why we do this locally in a test harness and definitely not on mainnet. Okay, part 4, the rollback scaffold. So the plane's engines are off, the alarms are blaring, and our invariant is totally violated. Time to deploy the fix. A rollback scaffold is exactly what it sounds like. It is your ultimate emergency reset button. It's a system that includes both binary snapshots of your program and account state snapshots. By pairing your saved prior state with the previous program binary, you can actually undo the damage and revert the blockchain back to exactly how it was before everything went wrong. So here's how the actual rescue plays out. First, our automated test suite calls that rollback.sh script we talked about. This script fires off a local command to redeploy the previous .so binary, that's our compiled Rust program, right back to the local validator. Then, using a handy little TypeScript helper, it restores the account snapshot, safely rewriting the account values back to their normal pre-disaster state. Section 5, verifying the rollback. But hold on, we are not out of the woods yet. You can't just run a bash script and cross your fingers. We need absolute cryptographic proof that the patient actually survived the operation. So we use a precise checklist. First, the program binary needs to match the prior build's exact SHA hash. Second, the account state, that value we accidentally zeroed out, must be perfectly restored to 42. And third, our test assertions need to come back clean with 0 failure alerts. If all 3 of those check out, the rescue is a total success. You know, during this whole recovery process, you kind of have to play the role of lead investigator. Capturing diagnostics is absolutely vital. You got to record the filtered program logs, grab hex or JSON dumps of the account from before and after the failure, note those exact binary SHA hashes, and thoroughly document the redeployment commands you used. You're building a definitive record of exactly how the crash happened and how you fixed it. And finally, Section 6, debug reports and next steps. We're going to take all that forensic evidence we just gathered from our drill and compile it into a debug report. A debug report is just a concise document capturing your reproduction steps, the diagnostics, and your rollback procedures. But what's amazing about this is that it takes a terrifying, hair-on-fire failure and turns it into a boring, actionable, and highly repeatable standard operating procedure for your whole engineering team. So the really big takeaway here, you've got to treat upgrades as stateful refactors. Changing the code isn't enough, you are fundamentally changing the state. This means you must always test the state transition path with positive cases and, crucially, negative cases. You have to break it in testing so it doesn't break in reality. I want to leave you with a somewhat provocative question. Think about this. If an upgrade failed on mainnet today, like right this second, do you have the exact binary and state snapshots to roll it back flawlessly? Because if the answer is no, well, you know exactly what you need to go build next. Master the art of the Web3 safety net, because in this space, your fallback plan is every bit as important as your primary code. Thank you so much for joining this explainer crafted by Forge College. Please head over to forge.college to master the art of the Web3 safety net. Grab some detailed debug report templates and check out our other expert developer tracks. Until next time, keep your invariants true and your rollbacks ready.